Okay, here we are with our next video, and we have to prove the relationship between left and right limit and the whole limit. Okay, and I give immediately the theorem. And this is an important theorem that will be used extensively in the course and in general in the study of the analysis. And so the name of this theorem, if you want to give it a name, is the relationship between left and right limit and the full limit. Relationship is very simple, but however, in stating the hypothesis of the theorem, we must be somewhat careful. And as usual, we have a domain E in R, E not empty, X bar in the E. So the fact that E is not empty should be somewhat accepted for every statement, I say. I don't like to fall into the logic of the fundamentals of analysis because this is not the scope of the course, but however, when E is equal to the empty set, you easily fall into paradoxes that I don't want to touch here. So in general, when I consider a set, I always mean a non-empty set. In this time I wrote it. However, E, a subset of R, not empty. X bar is an accumulation point of E, and it is a real point. So X bar is real point, is not plus infinity or minus infinity, and moreover, I ask X bar to be an accumulation point both from the left and from the right. So from the right means that there exists a U1 neighborhood, right neighborhood of X bar, such that the intersection between U1 and the domain, possibly excluding the point X bar, is not empty. And the same from the left. U2 is a left neighborhood of the same point X bar, and here you have that U2 in the section E minus X bar is not empty. Then it is true that the limit for X going to X bar of F is equal to L if and only if, so it is a perfect equivalent, both the limits from the right and from the left are equal to L. So the proof is quite immediate. And we start from the direct implication that says, let us suppose first that the limit for X going to X bar of F of X is equal to L. Then we want to prove that both, I specify it better. So we aim at proving that both right and left limit of f as x goes to x bar exist and equal L. So I have to apply the definition of right and left limit. So first of all, I have to start from V, which is an arbitrary neighborhood of L. I specify here that I never said that L must be a real number. L can be plus infinity or minus infinity. So when I say a neighborhood of plus infinity, I mean a set that contains a half line, a right half line in the real line. So be careful about that. Okay, V is a generic neighborhood of L, regardless of the fact that L is finite or not. And by definition of limit, because we are supposing that the limit exists here, so from the definition of limit, we know that there exists U, neighborhood of x bar, such that f of U intersection E, excluded possibly the point x bar, is a subset of V. Okay, just the definition of limit. Now, let us define a set U plus, which is U intersection the right half line starting from x bar. What is U plus? So if this is the half line here, U is a neighborhood of x bar. Let me consider a sort of right neighborhood of x bar. Then we intersect with a half line starting from x bar and going to plus infinity. So what we find here, this is the half line, and the intersection is this. So I specify the picture. The red set is U, the brown set is x bar plus infinity, so that the blue set at the end is U intersection x bar plus infinity. And notice that this intersection results on being a right neighborhood of x bar. So this is an element of U x bar plus. Moreover, we have that U plus is contained in U, and therefore U plus intersection E minus x bar is contained in the U intersection E minus x bar. Then when I study the image of this set, so when I consider the set F of U plus intersection E minus x bar, this will be contained in the image of the larger set F of U intersection E minus x bar that is contained in V. So what I proved is that for every neighborhood V of the limit point L, there exists a right neighborhood U plus of x bar that is mapped by F in V by the definition, so owing to the definition of right limit we get the following, that the limit for x going to x bar from the right of f of x is equal to L. Now we must prove the same thing for the left limit, and it is done in a pretty analogous way. So analogously, we define U minus to be equal to U intersection the left half line starting from x bar, and of course this is a left neighborhood of the point x bar. And again, as before, since U minus is contained in U, then the intersection of U minus with the domain E with a possible exclusion of the basis point x bar is contained in U intersection E minus x bar. That implies that f of U minus intersection E minus x bar is contained in f U intersection E minus x bar, which is contained in V. Therefore, the limit from the left of f of x as x goes to x bar is equal to L2. So, thanks to these two limits from the right and from the left, we conclude this part of the theorem, and the first part of the theorem is proved. So let us go to the second part of the theorem. This time we start by assuming that the left and right limits, so the limit for x going to x bar from the right of f of x is equal to the limit for x going to x bar from the left f of x is equal to L. We assume this, and we aim at proving that the limit for x going to x bar of f of x is equal to L. Again, we want to prove that this is the limit, so we have to start from the usual statement that says let V be a neighborhood of L, and of course, since the right limit is equal to L, this means that there exists a U plus, which is a right neighborhood of x bar, such that f of U plus intersection E minus x bar is a subset of V, and analogously, since also the left limit of f is equal to L, then there exists a U minus in U x bar minus such that f of U minus intersection E minus x bar is contained in V. Okay, now consider U equals the union of U plus and U minus. So picture here to understand what happens. Here we have x bar, and here we have the red neighborhood. Here is U minus. The purple, I know it is already purple, so let me change the brown neighborhood here is U plus. When I consider them together by making the union, this is U, and of course U is a full neighborhood of x bar. So this is a U x bar. So now we must understand what happens to the set U intersection E minus x bar when one applies the map U. And of course, this is U1 union, U plus union U minus intersection E minus x bar, and then by distributivity of the union with respect to the intersection, we have U plus intersection E minus x bar union U minus intersection E minus x bar. And so the image, so consider an element x in U intersection E minus x bar, then by definition of union we have that either x is in U plus intersection E minus x bar, or x is in U minus intersection E minus x bar. But in both cases, due to, let me call this to inclusions like asterisks, so due to asterisk, red asterisk, in both cases, x belongs to U intersection E minus x bar. So that, in both cases, f of x belongs to V. Then, for every neighborhood V of L, we found a neighborhood U of x bar that is mapped in V by U. Then we end up by saying that the limit for x going to x bar of f of x is equal to L, and this is the end of the proof. And this theorem contains the answer to our question. So in order to decide that L is a limit of a function for x going to x bar, is it sufficient to show that both the right and left limit share the same value L? And the answer is yes. What we found here is that the answer is yes. So, and in particular, vice versa, in order to prove that the limit does not exist, it is sufficient to show that the right and left limits are different. Okay, this is the answer. So, as an example, I take the sine function again. Consider f of x to be sine. We have, of course, that the limit for x going to 0 from the right of f of x is equal to 1, and the limit for x going to 0 from the left of f of x is equal to minus 1. And since the two limits are different, the conclusion is that the limit for x going to 0 of f of x does not exist. This is our conclusion. And so from here, the next topics that is naturally introduced by left and right limits is the topic on discontinuity. Okay, so let me write here discontinuity. It may be surprising at a first sight that I introduce discontinuity before introducing continuity, because one says at the end discontinuity is the opposite of continuity. So first introduce the positive term, continuity, and then the negative, discontinuity. First of all, it is not true, it is not fully true that discontinuity is the contrary of continuity. This is one of the not so rare cases in which the ordinary language does not really coincide with the mathematical language. One has to be careful to that. Second is that when studying the right and left limit, then discontinuity comes very naturally from this study. So because the idea, when we talk about discontinuity, the idea is using right and left limit in order to gain information about the local behavior local means near point x bar of a function. As we will see, these tools, left and right limit, are not so powerful to these purposes. In any case, this is a topic that it is in the book, so I am obliged to do it, and I will do it. So, as a notation, I will use this shorthand notation that is useful also for our chapters of analysis 1. The left and right limits of f of x for x going to x bar plus and minus will be denoted by f x bar plus minus. Okay, so the first option is that these two quantity f of x bar plus and f of x bar minus exist and coincide. And they are real. So lim x going x bar plus minus f of x is equal to L in R, or due to the theorem equivalently, the whole limit for x going to x bar of f of x is equal to L. In this case, this case, one says that we are in presence of a eliminable discontinuity. What does it mean that we are in presence of an eliminable discontinuity? Is that we can define a new function f tilde of x, which is equal to f of x for x different from x bar, and 12 for x equal to x bar. And so this function extends the function f to the point x bar, assuming at x bar the value of the limit. F is called the continuous extension. f tilde, sorry, is called the continuous extension of f to the point x bar. So it is continuous. We will complete this notion when studying continuity. What I really forgot to tell you here is that we start from the fact that an f is not defined at x bar. It will be clearer now by this example, and also that this discontinuity, the eliminable discontinuity, is also called as discontinuity of the first kind. As an example, we consider the function f of x is equal to sine of x over x. The natural domain, so the maximal domain in which the analytical expression here is properly defined, is r minus 0. This is E, and so 0 is not defined here, but we know that the limit for x going to x bar of f of x is equal to 1. So defining f tilde of x as sine of x over x for x different from 0, and 1 for x equal to 0, we construct the continuous extension of f to the point 0, or to the whole of R. And so to let you understand what we changed to f by introducing this f tilde, the picture so this is sine of x over x. Sine of x over x is not defined here. So I portrayed here this sort of hole with a circle here. But f tilde is defined here. Okay, good. So the second type of discontinuity is the following, that the right and left limit f of x bar plus and f of x bar minus are both existing, are real, but do not coincide. And one says that we are in presence of a jump or discontinuity of the second kind. What is the kind of the discontinuity? It is always, it depends on books. So I'm really not very fond with this sort of classification, but however, when you say a jump, it is clear what you mean, and the example, typical example is the sine function. This is sine of x, and the quantity sigma f of x bar, which is the difference between the right limit and the left limit, this is called the jump of f. At x bar. And the last is the third kind of discontinuity. In all other cases, which means when at least one of the two left and right limits do not exist, or they are infinite and so on, in all other cases, one says that the discontinuity is of the third kind. In other books it is a bit different. In other books, one says that the eliminable discontinuities is of the third kind, and the jump is a third kind. And so the other second kind. This is not very important. Tell me jump and so on. Oh, the example here, for instance, you can say that f of x is equal to 1 over x, e, the domain is r minus 0, and here you have this graph for the function 1, 2. These two branches of the hyperbola, so you have that f of x bar plus is equal to plus infinity, and f of x bar minus is equal to minus infinity. And now, okay, let's go to the next video for continuity.